We have here two very different examples of ultrasound machines. On the left, we have a typical large machine on a trolley with a full panoply of controls, storage, all sorts of ancillary things, etc. But obviously this is something that you would only find in a major department, in a hospital, etc. On the right, we have something very different. This is a pocketable, portable ultrasound machine. The probe contains a large amount of electronics, and it then connects to a normal smartphone. You download the manufacturer's software to that smartphone, and it becomes a complete ultrasound machine. So this is a relatively recent development, and there are now several manufacturers making machines like this. Obviously, there's going to be an enormous difference between these two machines. And yet, the important thing is that the fundamentals of how ultrasound images are made are the same between these two. And that's what I'm going to be describing in this talk. The basics of the processing of the ultrasound image, which are pretty much the same in all machines. So as we've just seen, ultrasound machines vary in size from large full-sized units to very compact handheld ones. The basic principles, as I said, are essentially the same, but the way in which the processing is implemented clearly differs depending on the type of machine. Every ultrasound machine has a small amount of analog electronics, which means electronics that processes time-varying voltages. Obviously, the transmitted signal is a time-varying voltage, and the received echoes are time-varying voltages. However, they are very rapidly digitized, and all the rest of the processing in the machine is then done by digital electronics under software control. Whenever you interact with controls, that's interpreted by the software, and appropriate commands are sent to the various processing modules to respond to your changes of the controls. Another point I'd like to make about ultrasound is that you will find variations in terminology. I try to use generic terminology as far as possible, but even that is a little variable. Many companies have come up with their own names for particular functions. So you'll probably find that you'll learn to do some translation from the generic terms to the particular corporate terms used by different manufacturers. Lastly, I would like to describe what happens at the start of any given examination. You select an appropriate probe depending on the kind of examination you're doing. You then enter patient details and select from a menu the type of examination you're doing. For example, if you're doing an abdominal examination, you may get a choice of, you may be able to choose, for example, an adult renal scan. The point of doing this is that the machine then presets all of the different variables in the machine to appropriate settings. So it will set the frequency, the amount of amplification, the depth of the image, a whole lot of the various parameters that can be varied will be adjusted to the optimum for a standard examination of that type. So you'll normally have a very good starting point for the setting of the controls. However, it's important to realize that you need to check some of them before you begin scanning, or at least at the very beginning of the scan, to make sure they really are optimized for the individual patient. Similarly, some of the controls will need to be adjusted and readjusted as you're going through the examination. This rather daunting block diagram is just showing you the various elements within the ultrasound machine, the functional elements, which I'll be going through in more detail in this and the next lecture. But let me just briefly go through this block diagram while we have it here. At the top in red, we have the transmit function. So we have the electronics that's actually generating the transmit pulse. That is then delivered to the probe through the delays in the transmit beamformer electronics, which I spoke about earlier. The returning echoes pass through the delays in the receive beamformer in order to produce a focused beam. And we then have an echo signal, which must be amplified because it is very, very low level, and it could well be degraded unless it was amplified immediately. So the received echo is amplified in an amplifier, and then we have a function called TGC, which I'll be explaining, followed by compression, and then a scan converter, which formats the echo data appropriately for the image so that it can be stored in the image memory. Once a complete image has been built up in the image memory, that is displayed. It can also, of course, be saved, stored, annotated, and so on. So we'll go through all of this in more detail now. I just have one thing I'd like to talk about in connection with the probe. I've discussed the transducer, which is the active element within the probe, and I've talked about the probe itself and its construction. I want to just talk briefly about the connector, which connects the probe to the ultrasound machine, and the cable, which goes between that connector and the probe itself. You'll see the connector on the right, and you'll see that it's got 128 small individual connectors, and each one of those will be connected to one of the elements that is active at a particular time in the probe itself. So there are 128 connectors because the machine is using 128 transducer elements at any one time to transmit and receive. The cables connecting the probe to this connector are shielded cables, which means every one of the 128 cables has a central conductor and then insulation, and then has a metal sheath around it to shield it from electrical interference, and then another insulating layer. So they're very similar, in fact, to the cables that cable TV comes on, or the sort of thing that you connect to your television antenna. There are 128 of these in the cable, and my point is that the cable is therefore quite heavy and bulky. This is important from an ergonomic point of view, that over a period of time, particularly if you're doing a lot of scanning, this can be a fair weight on your wrist and arm, and therefore you need to think about ways to support as much as possible the weight of the cable. Many machines have some sort of hook or some sort of arrangement to take as much of the weight of the cable off you as possible. But this is an important consideration if you do a lot of scanning. Now I'll talk about the transmitter and the beamformers. So the transmitter generates the transmit pulse. So it's a set of electronics, and it has to set and determine the ultrasound frequency, the amplitude of the pulse, the duration of the pulse, and the pulse repetition frequency, the rate at which the transmit pulses are being generated and sent out. So all of those things are controlled by the transmitter, of course under software control. We then have the transmit beamformer, which contains the delays that I've spoken about before. There are two controls that you have which will affect the transmit beamformer. One of these is setting the depth of the focus. So you set the depth at which the transmitted beam is focused. You may also steer the ultrasound beam. This is particularly the case in Doppler ultrasound, both pulsed Doppler and color Doppler, and also in echocardiography it applies to continuous wave Doppler as well. Then we finally have the receive beamformer, which takes the received echoes from the individual elements and combines them together, but by delaying them first of all in order to form a focused beam. The user has no controls over the receive beamformer because you may remember it's a dynamic beamformer which is continually adjusting itself so that it is always focused correctly at the depth the echoes are coming from, moment by moment. So you can see that the main controls that you'll have here would be the output control on the transmitter. You can turn up and down the amount of transmitted power And then with the beamformer, we have the depth of focus and also the question of whether or not you're going to steer the beam in some direction other than the usual. Now we have the amplifier. As I mentioned, the echo signal is very small, and therefore it's important to amplify it immediately, because every electronic device has some electronic noise which will interfere or degrade the quality of the echo signal. And so the sooner the machine can amplify the echo signal, the better, because then that minimizes the impact of this electronic noise. So an amplifier simply makes the echo signal larger, and it does this regardless of what depth the echo is coming from. So it's referred to as the overall gain, or sometimes the B gain or B mode gain control. So you can increase and decrease the amount of gain or amplification in order to get the right level of brightness in your image. Decreasing the gain control will of course make the entire image darker, increasing it will make the whole image brighter. Now we have a more complex gain function referred to as the TGC, or time gain compensation. The reason for this is that it compensates for the fact that the echo signal gets progressively weaker with depth due to attenuation. So the TGC is compensating for attenuation. The machine calculates the expected amount of attenuation, assuming that it has average soft tissue in the image. So the machine automatically increases the gain, that is the amount of amplification, microsecond by microsecond to compensate for average attenuation. Now this of course is not going to be perfect because tissues are variable. So it's important that you have a manual TGC function as well to allow you to compensate for variations, both within the one patient and also between patients. The manual TGC, as shown in the diagram on the bottom right here, usually consists of a series of sliders. Sliding these to the left reduces the gain, sliding them to the right increases the gain. Each slider corresponds to a different depth. So the top slider would be varying the gain in the most superficial tissues. The bottom slider would be varying the gain in the deepest of tissues. And so you can adjust these sliders to vary the rate at which the gain is going to change with depth. And the aim of this is to give you an image where uniform tissues will look the same at different depths. I'll show you an example. Here we have two images of a liver. On the left, the TGC has not been optimized. You can see that the image fades away with depth. The echoes are bright initially, but then they become less and less bright until we lose the echoes entirely from the liver. We do see the very strong echoes from the diaphragm, for example, because it's a very strong reflector, but we lose the soft tissue echoes as we get to greater depths. On the right, the TGC controls have been adjusted. So basically the deeper controls were slid to the right to increase the gain at greater depths. The controls for the most superficial part of the image were slid a little bit to the left to reduce the gain because it was too bright. If you look in the image at the left, the echoes superficially are too bright to be able to see detail. So on the right, those sliders have been adjusted by the user of the machine to produce a very nice uniform appearance in this liver. And that's the aim of the TGC control, to get uniform tissues to look uniform. Now we come to a very different concept, and that's the concept of dynamic range. Dynamic range is a general term used to refer to a range of variation of something. And in our case, we use the dynamic range term to talk about the variation of echo intensity values. So I can talk about the dynamic range of the received echoes that the machine actually detects. And this is going to be very large. Even after the TGC function has corrected for this dynamic range, there's still likely to be a range of about 1 million to 1 in echo strengths. Now, the dynamic range is measured by taking the ratio of the maximum intensity of the echo signal and dividing that by the intensity of the minimum echo signal. So we're dividing the largest by the smallest. That will just be a simple ratio, so that's just a pure number. Because it's such a big number and can vary so much, it's conventional to measure it in logarithmic terms using decibels. So we take that ratio of the strongest to the weakest echo intensities, take the logarithm of that and multiply by 10, and that then gives us a measure of the dynamic range expressed in decibels. So the dynamic range is typically 60 decibels or more. Perhaps in modern machines it's more like 70 decibels. So 60 decibels would be a ratio of 1 million, 70 decibels would be a ratio of 10 million. So you can see there is a huge range of variation of echo strengths. We're going to display this on the screen as variations of the intensity of the grayscale. So we're going to have a dot representing each echo, and the brightness of that dot will be varied to represent the strength of the echo. The dynamic range of the display, and of our eyes in fact as well, is at best around 30 decibels. We can only see a range of, at most, 1,000 different levels of brightness, probably less than that. So there is an enormous mismatch between the dynamic range of the echo signals we're trying to display and the dynamic range that can be displayed on the screen. The machine therefore has what's called a dynamic range compression function, which basically reduces the dynamic range of the echo signals to match up with what can be displayed. This is normally expressed in a compression curve, which I'll show you in the next slide. So this compression curve shows us echo intensity on the horizontal axis and displayed intensity on the vertical axis. In both cases, I'm using decibel ranges here, so they're using logarithmic scales for both of these vertical and horizontal axes. Now I should point out that because these are decibel ranges, in both cases the 0 decibel point simply is the weakest possible value, and then we have decibel values above that weakest possible value. So 0 dB on the horizontal axis would be the weakest detectable echo. And then the 60 dB point would be an echo 60 dB stronger than that weakest echo, so 1,000,000 times stronger in intensity than that weakest echo. On the vertical axis, again, 0 is the weakest non-black value that we can see on the screen, and the 30 decibel point would be white. The green line shows us how echo intensities are mapped into displayed intensities on the screen. For example, if you follow the red dotted line, if I had an echo with an intensity of 30 decibels, then we follow that vertically up to the green line and then go horizontally across to the vertical axis, and we see that this would be displayed with a value of around 25 decibels. You'll notice something here, that this curve flattens off as it gets to the higher intensity values. This means that all of the strong echoes, from 30 decibels up to 60 decibels, are going to be squeezed into a narrow range of brightnesses, going from a pale grey to pure white. So all of the strong echoes are going to look quite similar. They're all going to be bright in the image. And the purpose of this is to allow us to see variations in the lower level echoes, to see variations in the intensity of those lower level echoes. The reason for this is because that's far more important clinically. That's far more useful and valuable clinically. So that's the way this compression curve is designed. It's designed to spread out the variations of low-level echo intensity so that we can actually see them and perceive them on the screen. And the cost of doing that is to make the stronger echoes all look very similar. So roughly speaking, the lower 30 decibels of the echoes correspond to scattered echoes coming from soft tissue, and the stronger echoes above that 30 decibel point are going to be predominantly from reflections from tissue interfaces. So what we're saying is that the most important thing is to be able to display variations in soft tissue echoes produced by scattering. Now this would be referred to as a 60 decibel compression curve, because the full range of 60 decibels of echoes is being displayed and has been spread across the display range of the machine's display. So we're seeing all of the echoes in that complete dynamic range. If the machine had a dynamic range of 70 decibels, that would mean echoes covering a range of 70 decibels were being displayed. Sometimes it's useful to have a more limited dynamic range displayed. So here we have a dynamic range compression curve which goes from that 20 decibel point up to the 60 decibel point. What this means is that echoes between the 0 and 20 dB points are not displayed. They're being suppressed. They're not being shown in the image. So then we have only 40 decibels in total, from 20 up to 60, 40 decibels of echo signal dynamic range being displayed. So this would be referred to as a 40 decibel dynamic range. Let's just talk for a moment about why you would want to suppress low-level echoes like this. Perhaps the best way to do this is to look at an example. Here we have an image of the liver displayed on the left with the lowest dynamic range that the machine can, a setting that the machine has. And we can see a couple of things about this image. The arrow highlights the fact that we're actually losing echoes deep in because the gain isn't quite sufficient and those echoes are too low level, they're not being displayed. The second thing is that the soft tissue has a fairly grainy appearance to it. We can see the speckle pattern quite distinctly. The other thing to notice is that fluid-filled areas are relatively free of artifact echoes. Now let's have a look at the same liver, imaged now with the dynamic range setting at the maximum setting that the machine has. So now you'll see there's no dropout. We can see the echoes all the way to the maximum depth of the image. So we're not losing any important echoes. Secondly, the soft tissue now looks rather smoother because we don't get so much black and white sort of effect. It's more of a more uniform grey appearance, so it looks rather different. And then finally, as highlighted by the arrows, now we're seeing quite a lot of artifact echoes within fluid-filled areas. So that's the primary difference. That's the reason why sometimes low dynamic range settings are used. The reason is to suppress these low-level echoes which might otherwise fall into fluid-filled areas and be a nuisance. And it's doing it on the basis that those artifact echoes are likely to be quite low level compared to most of the other echoes in the image. Two areas where it's likely that low dynamic range is used for this reason would be vascular and cardiac. So the machine is likely to automatically select a lower dynamic range setting when doing vascular and cardiac ultrasound in order to minimize the appearance of artifact echoes within fluid-filled areas. So I have spoken about the probe and in particular about the cable. I talked about the transmitter and the transmit and receive beamformers. I talked about the amplifier. The only control you have on the amplifier, by the way, is just the overall gain control. I spoke about the TGC, the fact that the machine has an internal TGC function correcting for the attenuation of normal tissue, and then you have a set of sliders, which is the manual TGC function, which you use to fine-tune the image to correct for variations between different tissues and different patients. And then finally, I've explained the idea of dynamic range and the idea of the machine compressing the dynamic range of the echo signal to match what can be displayed. There are still some further functions to talk about, and we'll cover those in the next lecture.